So, hello guys. Today we're going to discuss about electroanalytical chemistry. So, electroanalytical methods are a class of techniques in analytical chemistry which study an analyte by measuring the potential in volts and or current in amperes in an electrochemical cell containing the analyte. The three main categories are potentiometry, or the difference in electrode potentials; coulometry, the cell's current is measured over time; and voltammetry, where the cell's current is measured while actively altering the cell's potential. A galvanic cell transforms the energy released by a spontaneous redox reaction into electrical energy that can be used to perform work. The oxidative and reductive half reactions usually occur in separate compartments that are connected by an external electrical circuit. In addition, a second connection that allows ions to flow between the compartments is necessary to maintain electrical neutrality. The potential difference between the electrodes, which is the voltage, causes electrons to flow from the reductant to the oxidant through the external circuit, generating an electrical current. In an electrolytic cell, an external source of electrical energy is used to generate a potential difference between the electrodes that forces electrons to flow, driving a non-spontaneous redox reaction. Only a single compartment is employed in most applications. In both kinds of electrochemical cells, the anode is the electrode at which the oxidation half reaction occurs, and the cathode is the electrode at which the reduction half reaction occurs. For an irreversible electrode like the Daniell cell, it is called as such because the reaction takes place in the electrode itself. The Daniell cell has no salt bridge, it only has a porous barrier for a salt bridge. The two terminals of anode and of cathode and the porous barrier in between are the five terminals of a Daniell cell. For the zinc sulfate terminal, the electric potential of zinc sulfate is higher than that of zinc. The electric potential is denoted by the symbol Phi. For the copper 2 sulfate terminal, the electric potential of copper is greater. For the copper, zinc has a greater electric potential since zinc is more reactive than copper. Thus, copper has a lesser tendency to transfer its electrons. There's an equal electric copper terminal, and the same goes for zinc sulfate copper 2 sulfate terminal. Equating all of these electric potentials to get the cell electromotive force or cell EMF in all junctions or terminals, we will get the equation on the second photo. The electric potentials of copper 2 sulfate and zinc sulfate will cancel out, giving us a positive cell EMF or epsilon greater than 0. Once the circuit is closed, redox reaction will take place. Now, what if the Daniell cell was an electrolytic cell? Copper will simply be oxidized while zinc will be reduced. The cell EMF is the difference between the electric potential of the right terminal and the electric potential of the left. The cell reaction is defined to involve oxidation on the left and reduction at the electrode on the right. A positive EMF for a cell diagram means the cell reaction corresponding to this diagram will occur spontaneously when the cell is connected to a lot. A reversible electrode is a metallic electrode that will dissolve when a current is passed from it into a solution and will have metal plated on it from the solution when the current is passed in the reverse direction. Getting one value of electric potential in an electrochemical cell is sufficient since the oxidation potential of a half reaction is the negative of the reduction potential for the reverse of that reaction. However, the electrode potential cannot be determined in isolation, but in a reaction with some other electrode. The electrode potential depends upon the concentrations of the substances, the temperature, and the pressure in the case of a gas electrode. First, we measure the potentials with respect to standard hydrogen electrode. It is the nature of electric potential that the zero of potential is arbitrary. It is the difference in potential which has practical consequence. Tabulating all electrode potentials with respect to the same standard electrode provides a practical working framework for a wide range of calculations and predictions. The standard hydrogen electrode is assigned a potential of 0 volt. Second, secure the standard of thermodynamic conditions for the measurement of the potentials. The standard electrode potentials are customarily determined at solute concentrations of 1 molar, gas pressure of 1 atmosphere, and a standard temperature which is usually 25 degrees Celsius or 273 Kelvin. The standard cell potential is denoted by a degree sign as a superscript. To summarize, E cell is measured against standard hydrogen electrode. The concentration should be 1 molar, pressure is equal to 1 atmosphere, temperature is equal to 25 degrees Celsius, and the example in this slide shows some values for standard cell potentials. Gibbs free energy is also related to E under general conditions, standard or not, as shown in equation 1. Hence, when E is positive, the reaction is spontaneous, and when E is negative, the reaction is non-spontaneous. From thermodynamics, the Gibbs free energy change under non-standard conditions can be related to the Gibbs energy change under standard equations via equation 2. Substituting equation 1 into 2, we get equation 3. And as shown here, dividing both sides of the equation by NF, we get equation 4. Equation 6, or the last equation, signifies that the electric potential of a cell depends upon the reaction quotient Q of the reaction. Electric double layer is the phenomenon playing a fundamental role in the mechanism of the electrostatic stabilization of colloids. Colloidal particles gain negative electric charge when negatively charged ions of the dispersion medium are adsorbed on the particle's surface. A negatively charged particle attracts the positive counterions surrounding the particle. Electric double layer is the layer surrounding a particle of the dispersed phase and including the ions adsorbed on the particle surface and the film of the countercharged dispersion medium. The electric double layer is electrically neutral. To initiate the electrochemical reactions in the cell, potential value, which includes the ohmic drop or the negative IR due to the cell media resistance, should be applied to the cell. In other words, while applying potential to a cell equal to the equilibrium potential, no chemical reactions and as a result, no current will flow in the cell. Therefore, the value of applied cell potential, which considers the ohmic drops and loss of potential due to activation and concentration over potentials, can be expressed as the equation below. In many electrode reactions, electrodes do not behave ideally, as sometimes the gaseous products obtained gets absorbed on the electrode surface, which hinders the electrode reactions. This slowdown of electrode reactions can be overcome by some extra potential, and this potential is known as overpotential. So as we can read from this slide, the reaction or activation polarization is the overpotential caused by overcoming the energy barrier of the slow intermediate reaction. The common cause of these is the hydrogen formation and the evolution at the cathode surface. First, there is the reduction of the hydrogen ions resulted in formation of atomic hydrogen on the cathode surface. Next, the formation of molecules of gaseous hydrogen. Lastly, the formation of hydrogen bubbles. The cathode is polarized by the hydrogen atoms producing a film covering the cathode surface. The film affects the process kinetic. It slows down the reaction between the electrons and hydrogen ions dissolving in the electrolyte. At the equilibrium or non-polarized state, the rates of oxidation and reduction reactions proceeding at any electrode are equal. For example, the ions of copper are receiving electrons on the electrode surface and transfer from the electrolyte to the copper deposit. In parallel, the same number of copper atoms give up their electrons and dissolve in the electrolyte. In the most common forms of potentiometry, two different types of electrodes are used. The potential of the indicator electrode varies depending on the concentration of the analyte, while the potential of the reference electrode is constant. Potentiometry is probably the most frequently used electroanalytical method. It can be divided into two categories on the basis of the nature of the indicator electrode. If the electrode is a metal or other conductive material that is chemically and physically inert when placed in the analyte, it reflects the potential of the bulk solution into which it is dipped. Indicator electrodes are paired with a reference electrode and can be used to determine the concentrations of targeted analytes in a solution. The cell potential will be directly influenced by the target analyte concentration. Metal indicator electrodes of the first kind require a pure metal of that analyte that can be used as the indicator electrode. There are a limited number of metals appropriate for such reactions, such as silver, bismuth, cadmium, copper, mercury, lead, tin, titanium, and zinc. Due to the simplicity of the redox reaction, the potential for such cells can be reduced to a simple equation containing a single constant and dependent on the concentration of the metal ion. In order to use an electrode of the first kind, one would first need to calibrate the instrument with known concentrations of the metal ion in order to determine the value of the constant K. With the constant determined, unknown solutions containing the metal ion could be measured and the cell potential directly converted to A concentration. Metal indicator electrodes of the second kind. The electrodes that can be used as electrodes of the first kind can also be used to determine the concentration of other species in a solution, provided that the metal ions interact with this new analyte. These are termed electrodes of the second kind if there is an equilibrium between the metal ion and the analyte. The potential for the cell can be expressed in terms of that analyte. The SCE and AgCl reference electrodes are electrodes of the second kind. There are several ways that a metal indicator electrode of the second kind can be used to quantify an interacting ion. In all cases, the original concentration of the metal ions needs to be known prior to the analysis. Uses of these electrodes include titrations and direct analysis of analyte solutions.